Hello, everyone. So, I'm gonna start basically recording my lectures in two-part videos. Part one, always going to be the concept of the chapter. So I basically will be going over the lecture notes, talking about the concept of the chapter, giving you simple examples and things like that. And in part two, which will be a separate file, I'm going to then solve most of the problems that we have in the chapter. So that's why, hopefully the video lectures, in that case, if it's two parts, right, it will be maybe hour and a half each. So it will be easier for you guys to watch them, let's say separately and things like that. So in any case, so we're going to start with chapter 5. Chapter 5 is something that we covered a little bit of last time. So I talked about static equilibrium. I gave you a couple of examples. I briefly mentioned the dynamic, so sort of like, let's say, the Newton's second law application and things like that. So, but in any way, we're gonna go back and start this chapter pretty much from the beginning. And so let me then share my screen. So from here, we're going to start with basically going back and summarizing some of the things we have in this chapter, and then pretty much going from the beginning, covering the entire thing. Again, this video will be strictly the concept in terms of very simple examples, and then the second part video will be for the examples, in this chapter, or in this, lecture notes that I have. All right, so anyways, this chapter 5 is continuation of chapter 4. In chapter 4, we learn about Newton's laws of motion. We identify different type of forces, what is a force, how to represent the force, how to add forces together, and free body diagram. We also learned that. So in this chapter, then we're going to be applying all that to solve problems. But in any case, so in terms of some of the things, obviously, we'll be coming back to. So in this chapter, we're going to do a lot of applications of Newton's first law, second law, and the third law. And in the process, again, summarize those things, right? And we're going to look at a few other new type of forces, you can say, that we haven't covered in chapter 4. And those are elastic forces, or let's say spring force, for example, and a drag force, which is due to air resistance, and more detailed look at the friction force. All right, so let's start with Newton's first law. Remember, the first law give us the condition of what we call equilibrium. Remember, equilibrium represents object with no acceleration. So that's the kind of the key that we could look at it. Now, when there is no acceleration equals 0, remember, you can consider this, no acceleration from 2 point of views. Point of view of kinematics and point of view of dynamics, which means Newtonian dynamics. Remember, kinematics, so if you kind of look at it in terms of kinematics, no acceleration meant velocity doesn't change, right? It's constant. That's what it means. No change in your velocity. From the dynamics point of view, by the way, again, dynamics means that Newtonian forces. That's kind of what I mean by dynamics. From the dynamics point of view, this means that if acceleration is 0, is due to the fact that forces acting on the object is 0. That means no net force. And obviously, since we are treating force as a vector, we are considering no net force in the x direction, no net force in a y direction, right? So that's kind of what we are looking at. That means all the forces in the x direction cancel, all the forces in y direction cancel. And basically the result of that is no acceleration in the system. Well, if there is no acceleration, your object will not be changing its speed or changing its velocity. All right, so one of the things we have here is you can kind of break down the equilibrium itself, right? So here's an equilibrium into two categories. So here's a static equilibrium, and here's dynamic equilibrium. Again, dynamic equilibrium, do not confuse with the Newtonian dynamics. So static equilibrium, again, remember equilibrium, basically what we just talked about here. This is, condition of equilibrium, means that no acceleration in the system because there are no forces, or all the forces cancel each other. But you can have two conditions. You can have equilibrium where your object has no velocity, basically is at rest. Okay, so your object is at rest with no velocity. We call this static equilibrium. That means if it's at rest right now, it's going to be at rest 5 minutes later, it's going to be at rest 10 minutes later, right? You can see, right? That means at any instant when you look at its velocity, it's zero. So it is constant, but it is zero. Then dynamic equilibrium is when you have a non-zero velocity. That means object is in motion, right? Object in motion, but maintains that particular velocity it has. It's not going to speed up. It's not going to slow down. It's not going to change the direction. It has constant speed or constant velocity. Same speed, same direction the entire time. But, remember, in order for you to change your speed or change your direction, we talked about that you need acceleration. But if there is no acceleration, because it's in equilibrium, right? That means you're always going to continue moving the same speed, same direction. This was what we talked about in chapter 4, technically, right? So this is the condition for Newton's first law, which is the equilibrium. All right, so we did in class, we did few examples with the chandelier, I think, and then or the lamp, right? And then we did another example with the traffic light. And I will be going over those examples, in part 2 video. But remember, so that's kind of what we had for this. And we need to then kind of like, again, summarize it. Newton's first law gives us condition of equilibrium, which means that there's no acceleration because forces cancel each other in every direction, right? That means there are no component in X direction or the force, no component or the no net component, right? They all cancel. That means we have to always look at those two equations. So you're always looking at two equations, net force in a X, net force in a Y, but because let's say it's in equilibrium, they will sum up to 0. All right, so this is that example we will see later on, right? Actually, I guess that's one example I can do right now. So I forgot to delete this actually from the slide, but in any case, so here's, if you remember, we have a lamp which is suspended from a chain of negligible mass, and we want to find the tension force. Well, one of the things that you want to do with the force problems, identify object of interest. In this case, the lamp is our object. And once you identify your object of interest, you want to identify the agents. Well, there are two agents, Earth pulling it down, and because it is connected by a chain, right? There's a tension force. Now you have tension force up, gravity down. So, but is the problem a problem of equilibrium or not? Well, most of the time, the wording in a problem will give you that hint. And in this case, it says it's suspended, which means, the object is, with no velocity, right? Is in what we call static equilibrium. All right. So every problem has three parts, sort of like, 3 steps, not parts. So remember, step 1 will always be doing the free body diagram. Here's your X, here's your Y, this is your object. Then you have the gravitational force. Remember, we can call that weight. And then there's a tension, which is due to the chain. And step 2 will be to do the force table. And these are my forces, tension and weight. And remember, sum of all the forces acting on the object gives me net force. But what I want to look at here is I want to see if there is a forces in the x direction, forces in the y direction. But one thing I know here is if I'm doing net force in x, I know because it's suspended, this is 0. And the net force in the y direction, again, it is suspended, means that it's at rest, so this is also 0. In x direction, I have no forces. In y direction, I have tension, which is up, weight, which is down. So I put plus t minus w. And remember, I get two equations, which is step 3. Let me do it here, right? So step 3, equation 1, my horizontal forces added together. Well, I have none, so this is 0. Equation 2, my vertical forces added together. Well, here I have two forces, tension minus weight, right? Because they're in opposite direction. But because it's suspended, I get 0 as a net force, which means the tension as a force is equals to the weight of the lamp. So T equals W, right? And that's, my tension force. So it's a 100 Newton lamp, which means of its weight. That means the tension is also 100 Newton. All right, so that's kind of what we had for this particular example. Okay, so the next will be looking at the application of the Newton's second law. Remember, second law then gives us what happens when the forces don't cancel each other. And simply put, if the forces don't cancel in, let's say, horizontal direction, right? Well, the system accelerates then in that direction. That means, let's say you have a box that has one force of 20 newtons in this direction and another force of 10 newtons. So let's say this is x hat, this is then negative x hat, right? So you have those two forces acting on it. So technically I have to make this twice as much, right? Because it's double the magnitude. See, if I'm looking at this and doing net force in x direction, then I will be 20 newtons, which is F1, minus 10 newtons, which is F2. You can see my net force is 10 newtons, which means they don't cancel each other. That means I have a horizontal, you can say, right, horizontal force, which is 10 newtons. So what happens to my system? Well, according to the second law, I'm going to get an acceleration in that direction. And then let's say taking the mass of this object, right, for example, as, 10 kilograms, then what I can see here is, according to Newton's second law, net force in x direction equals mass times horizontal acceleration. Then from here I can calculate then the acceleration, which is net force divided by the mass, 10 newtons, which basically what I got from here, right? Divided by mass of 10 kilograms, I get 1 meter per second square acceleration. That means object will be speeding up in the direction of that particular, let's say in this case, right, in a horizontal direction. Well, that means if the forces in x direction don't cancel, you're going to get a net force, which is going to give you the acceleration. And that's kind of what the second law represents. When you are pulling or pushing in one direction stronger than another one, your system not just going to move, but going to accelerate. All right. But obviously, one of the things we're going to do here is taking this equation as our, let's say starting point. And the first thing we do here is we break it down into components. That means in reality, we're always going to be looking at two equations. Again, equation 1, equation 2, remember, right? Doesn't matter if it's equilibrium or if it's, Newton's second law application, you always have two set of equations. Net force in x direction and net force in a y direction. So basically you get two equations from this particular type of motion. All right, so one of the important things that we're going to be doing in this chapter is also looking at Newton's third law application. Okay, and they are a little bit more difficult conceptually than, let's say, the Newton's first law or second law. And that's because whenever you are looking at the Newton's third law, we always consider interacting objects. That means you're going to have more than one object in the system, 2, 3, 4, or multiple objects, right? And they're always going to be connected sort of like next to, to one another. So for example, here's in front of you a picture of a truck, basically a toy truck, right? Pulling a car. And obviously it pulls the car by this rope, right? That means you have something that connects those two cars. And one thing we have here is when the truck is, imagine right now, you are driver of the truck, right? Both cars are at rest. You take the cable or the rope, right? You connect it to the car and then to your truck and then go sit in your truck and then start driving. As you speed up your truck, well, the car, because it is connected to the truck, it's also going to speed up with the truck. Now, how much your truck is speeding up, the same amount your car is speeding up. And that means the change in velocity for both the car and the truck will be the same, which means acceleration of the truck is the same as acceleration of the car. You can even look at the whole thing as a system of two interacting objects and say, okay, well, my system going to be accelerating at this rate, which is the same as the car or the truck, individually. That means we call this acceleration constraint. Any two interacting objects or any three interacting objects, right, will always have the same acceleration. Here's another example. Imagine you have block 1, you have block 2, you have block 3. So here's for example. So if I pull block 3 with some force, well, block B is just on its own, just sitting there. Well, if I apply force F to the right, block 3 will accelerate, 1 and 2 will just stay there because nobody's pushing or pulling them. But if I connect 2 and 3 and then apply that force, what I will have here is that then this force is going to make 3 accelerate, but because 3 and 2 connected together, so will the 2. That means block 2 and block 3 right now will accelerate. Okay, so in a way, one thing I have here is this force, right, is responsible directly pulling 3, but then 3, because it's connected to 2, will be responsible sort of for pulling, block 2. Okay. Now, one thing I will have here is, in this case, actually my acceleration will be a little bit less because see the force not only pulling 3, but also pulling 2, block 2. That means overall my acceleration will be less because see, when I'm looking at the acceleration, so this is the force divided by the mass. Well, see, before it was just mass of 3, but now because there's 2 and 3 connected, it's going to be mass of 3 plus mass of 2. You can see then overall acceleration of the system would decrease. Okay. Well, what if I then connect 1 and 2 together? Well, if I'm connecting 1 and 2 and 2 and 3 are connected already, then when I apply force, then all 3 will accelerate. And I can just say, okay, so then my acceleration equals applied force divided by the total mass. Because one thing I can do, I can assume that this is one whole system where force is pulling, the whole 3 objects together. And obviously you can see that acceleration now of the system will decrease, but still, if I'm looking at acceleration of 1, acceleration of 2, acceleration of 3, they're all going to be equal to one another. Less than before, let's say if it was just 2 or just 3, but they all have the same, shared acceleration. Anyway, this is known as acceleration constraint. That means any two, interacting or 3 interacting objects will have the same acceleration. Now, one thing I want to make sure that you guys here understand that this applied force, so for example, it's 10 newtons, okay? So when I'm looking at what accelerating, object 3, well, what accelerates object 3 is not just this 10 Newton net force, but sort of like, let's say it's 10 Newton net force is technically responsible, but there are other forces acting on 3. See, if I'm looking at 3, there's force, but there's also, see that there's a rope on this to the left side, right? So there's a rope over there. That means let's call this T3, which is the tension from that rope connected to the, box 3. And what will accelerate 3 is the net force, right? The difference between them. Now, if I'm looking at 2, so what's responsible for that acceleration of block 2? Well, at this point, this force of 10 newtons is actually not, directly pulling block 3. What happens here for the 2, I'm going to have to look at tension connected to 2, and then tension, let's say, on the other side, right? So let's say, I don't know, in this case, I can, this is actually one of the things I'm going to talk about next slide, so I'm kind of jumped ahead. But one thing we're going to see is that because there is one rope connecting 2 and 3, so technically there is just one tension over there. So the tension for that rope is the same, so I can just basically say this is tension 1, and then maybe here, this is, let's say, tension 2. Actually, I'm going to come back to this because I want to talk about the next slide before coming back to this problem. Well, maybe a few more slides later. So, all right, so here's what I have. Going back to that acceleration constraint. That means if you have 2 objects connected by a rope or a string or a cable, thing like that, and if you have a force acting on one, which basically pushes one of the blocks, then the other one will also be, pushed and accelerate because of that, interacting between A and B. So this is a very standard problem that we're seeing over here. You have 2 blocks, A and B connected by a string. So you can see that, and here we're going to assume no friction. That means surface exerts no friction. So what we get here is this, a string connected to A, and then the string goes over the pulley and then connected to B. Okay, and let's say I'm holding the system. That means I'm holding block A. Well, one of the things I have here is block A has this tension force, right? Basically, block A is being pulled to the right by this tension. Well, block B, it has 2 forces. Well, the gravity, the weight of B, right? And then the tension up, because, there's a tension over there. There's a rope over there, right? So what I do here is when I let go of block A, the gravity will pull down block B, and as block B is accelerating down, block A then will accelerate to the right because there is no friction. And one of the things we have here is if I look at acceleration of B compared to the acceleration of A, they will be the same. That means acceleration of A and B in their magnitude, right? Exactly the same. Even though one is horizontal, the other one is vertical, their magnitude will be the same because they are connected, by that string. Okay, so now one of the things we can see over here is 2 blocks and a string. And in reality, what we have here is as the block A accelerates, block B accelerates, well, so is the string. String is also accelerating. But here's one thing we have. When we're considering string and accelerating of the string, we want to make a very simple approximation that can allow us to make this, very important, let's say, conclusion. So let me kind of like use this particular picture to explain what I mean by that. You have 2 blocks, block A and block B, connected by this string. You can say one string connects A and B, and then you apply that force to block B. Again, remember, if you don't have this string, right? If you don't have the string, you apply that force, block B accelerates to the right, block A just sits there. But because then you have the string between them as you pull block B with that force, well, block A also accelerates. Okay. Now, what I have here is, so think like this. So here's B. It has this force to the right. Well, it has then the tension acting on B to the left. what I have here then, here's A, and A has then tension from the string acting to the right, because that's basically the tension in the string. That's what's going to be responsible for accelerating A to the right. So those are kind of like sort of free body diagrams. But then we also have sort of like, let's say, the string right in the middle. Well, here's the thing. Well, string will also, right, technically accelerate with them. And then what I have here is this. Well, if B, here's B, right? Like kind of sort of like what I have. So if B has a tension force, you can see, right, this tension force. This is the tension that string exerts on block B. Well, at the same time, action-reaction force, remember Newton's third law tells you that if the string pulls block B, well, block B pulls a string. So that means this is then the force that B exerts on the string. Now let's go back to block A. Here's block A, and this is the force that string exerts on block A, which is to the right. Well, again, action-reaction tells you that exactly same time, block A pulls the string to the left. That means if you're looking at the string, it has this. Here's a force that block B exerts on string. Here's the force that block A exerts on the string. So TB to the right, TA to the left. So let's say I'm just simplifying the subscript a little bit. Well, what I have here is this. So TB minus TA, right? Because, you know, one is to the right positive, one is to the left negative. So those are the two forces acting on the string. And what I know here is that this is the net force on the string itself, and is equals to mass of the string times acceleration of the string. Okay. And since the block A, block B, both of them accelerating because of that force, applied force here, right? The applied force F, well, so is the string. That means string itself is accelerating. But string can also only accelerate if tension V is greater than tension A, right? That means there's a non-zero net force acting on the string. V is stronger than A, so that means the string will accelerate to the right. But there's a problem with that. Not necessarily a problem, but let's say complication, let's say, which means that tension acting on V is different from the tension acting on A, even though it's the same rope. That means our life basically will be much more complicated if we assume that. What we do here is this. We assume that out of those three objects, block A, block B, and the string, we assume that mass of the string is so small. So for example, if block A is 5 kilogram, block B, I don't know, 8 kilogram, but maybe the string is like 5 grams or 2 grams. That means it's such a small value compared to the mass of the blocks that we can ignore it. We can say that basically it's almost zero. So we can say it's a massless string, and we can use this massless string approximation. Now, that means what I'm saying here is that if I take mass of the string to be zero, then see the equation that I have over here, right? Tension B minus tension A equals mass times acceleration. Well, if the mass is zero, so this whole thing is zero, which gives me TB minus TA equals zero. Well, that gives me that tension on both sides of the string is exactly the same. That means if I'm looking at the tension here, TA, and then looking at the tension here, TB, well, they're the same. They're equal to one another. And that's a very, very important and useful, tool to have. If I'm saying that I have a rope and the tension is the same everywhere along that, one rope, I can then always assume that tension that acts on A is the same as tension acts on B, and be able to use that, in my calculation. You can see in that example, when I do that, right, it makes my life much, much easier. So for example, here's block A connected to block B, and here's this rope. That means whatever tension force acting on A is the same that acting on B. Okay, so that's very useful. But for example, if I also have block C and there's another rope connecting B and C, then I cannot say that tension here is the same as tension over there. Tension for the string is no longer the same because it's a different rope. I mean, it's not the same as the tension between A and B. So that's why one thing I can do here is this. So let's say here's A, B, and C connected. So then what I can do here, maybe let's say T1, which is the tension in rope 1 that connects A and B. And T2 is then the tension in rope 2, which connects B and C. So that means because now I'm assuming that the tension everywhere same on the rope, then I can say T1 is the tension everywhere in rope 1. T2 is the same tension everywhere in rope 2. So that means I can just say T1 for rope 1, T2 for rope 2. Then for example, here's, let's say, going back to that. Let's say I have this force F acting on this block C. All right, so what do we have? Let's say there's a conceptual question. We have 3 blocks, A, B, and C. They're connected. Tension 1 connects A and B. Tension 2 connects B and C. And then you pull block C with the force F. Which one is the strongest one? So you have the force F, T1, let's say T2, right? And T1. Which force is the strongest? Is T2 the same as this applied force? Is T1 is the same as applied force? Does it mean that T1 and T2 are the same? So let's say that's a very good question. And, you will see an example and like that on homework. But let me kind of roughly give you an idea. One thing we can do here is this. See, when you apply force, this force F, see the force F pulls C, but then C connected to B, B connected to A. So technically force F is responsible for pulling all of those 3 blocks. That means I have to be strong enough to pull 3 blocks. Well, then let's look at tension 2. Well, tension 2 at the exactly same time is pulling 2 blocks. Well, then tension 1 is just pulling 1 block. What it means is that tension 2 doesn't have to be as strong as T2 or F because it's only pulling just 1 block. And T2 doesn't have to be, it has to be stronger than T1 because now it's pulling 2 blocks, but not as strong as F. That means the force is great, that this applied force is the greatest force, right, in terms of magnitude, and then it's greater than T2, and T2 is greater than T1 because T1 only pulls 1 block, T2 pulls 2 blocks, applied force has to pull 3 blocks, so it has to be the strongest. All right, so again, this approximation makes our life much easier because we are taking the tension along the same rope as constant. So that's why, coming back to this type of problems, then we can have this. You have a frictionless table, block A sitting on the table, and then you connect block A by a string, goes over the pulley, and connect it to block B. Well, one thing I have here is that there's a, the block B is hanging. That means there's a gravity acting on it, right? Weight of B. Well, even though there's a tension there, right? Remember, so now, because this is the same string exactly, even though if it goes over the pulley, it's still the same string, then I can say that tension that acting on A is the same as tension acting on B, right? So let's say, for example, this is tension acting on B, and here's tension acting on A, but they're the same. Now, this type of problems, we have 2 objects connected together, generally the best solved by breaking it down into 2 different systems. What I would do here is I break this down into system A. That means, remember, when you apply Newton's second law, or even Newton's first law, right? You are only looking at sort of like one point of interest or object of interest at a time. So in this case, block A, I want to know, if I want to know how the block A is moving or changing its motion, I'm going to take block A as object of interest, put that in my coordinate system, do all the forces acting on block A, and then figure out what happens to block A due to those forces. So that's why I'm going to take block A. I'm going to use this free body diagram where I put block A. So this is system A. I take block A, at the center of my interest, center of my coordinate system, right, at the origin. And then I can see the black A is at the surface. So there's a normal force on A. Say this normal force on A. Well, black A, well, is being pulled by gravity, so there's a weight on black A. So there are two vertical forces. Well, they happen to be canceling each other, right? But those are the two vertical forces. Well, I also see that there's a string pulling black A to the right, so there's a then tension, right? Tension, acting on black A. Well, that's my free body diagram for A. Then I go look at black B and say, okay, it's a system B. So, and I look at this independently from black A, where I can see that B is my object of interest at the center of my coordinate system. There is a gravitational force acting on B, pulling it down, and there's a tension acting on B, which is, in the direction of the string, right? And that's my free body diagram for B. But when I break it down into two systems, when I break down my problem into two systems, I always need to make sure that there's something linking those two systems. And then here we can say that what links them is the fact that they both have the same string connected. That means the tension acting on A and black B are the same. So that's why this is that link between those systems. Tension acting on A is the same as tension acting on B. Generally, you get two conditions satisfied. Here's condition 1, and here's condition 2. And that, remember, is because those two connected by a single rope, right? That means they're interacting objects, means connected together. Whatever acceleration I get for B, I'm going to have the same acceleration for A. In terms of the magnitude, they are going to be the same. All right, I'm going to do an example on this, and I will go over in detail in terms of how to solve problems like this. All right. So the next will be friction as a force. And what we have here is, we talked about friction before as a subtype of force that always acts in the opposite direction of the motion. But we're going to be going further in terms of defining what friction force is and type of forces, a type of friction forces, and how we can find the friction force and things like that. Right. So generally think of it like this. Surface gives you two forces. Well, assuming that object is on physical contact, physically on top of a surface, on the surface. So here's the box. See, there's a physical contact between box and the surface. And if that's the case, surface gives you one perpendicular force, perpendicular to the surface. And we've worked with that, right? So this guy over here, remember, that's a normal force, and it's always there. Object is at rest, object moving, object accelerating, constant speed, whatever it is, right? As long as the box on the surface, you always have a normal force. That's what prevents object to, fall, right? Because there's a gravity always. Remember, there's always gravity there. What prevents box, accelerating down is the surface, normal force, right? But then what we have also this. So there's this normal force, right? Yeah, so here's that normal force, which is perpendicular, right? Perpendicular to the surface. But there's also parallel to the surface force from the surface. And that is what we call a frictional force. So there's a frictional component, right? Friction force. That means you can see, right? The friction is the parallel to the surface force. You can think like it's, X component, right? And normally it's Y component. So technically, when I combine them together, right, you can see, right? So this is technically the contact force from the surface, okay? But we usually always just, look at normal force separately, friction force separately, and we rarely combine them to finding this contact force. We know that this contact force is the combination of normal and frictional forces, but we always just treat the, this contact force in terms of just separately normal force and separately friction. All right, so now think like this. Normal force has a very specific direction, always perpendicular to the surface. Friction force also has a, more or less specific direction. It always has to be parallel to the surface, always parallel to the surface. But then is it going to be to the left or to the right? In this case, for example, it depends, because it's a force that opposes, the motion of the object. See, in this example, those lines, right? They just basically mean that object is moving to the right. Well, if object is moving to the right because of this push or pull force, right? If there's some kind of applied force to the right, pushing the block to the right, well, then the surface is going to try to prevent it, try to oppose it. So the friction force will be to the left. That means it's going to be in the opposite direction of the applied force. That means friction force always going to be acting in the direction that try to prevent object motion, right? That means it's going to try to slow down always the object, or prevent the object moving at all. So that's kind of like the what we have with the friction. All right, so before we considered number of problems where the friction was 0, and that's usually when we say that surface is frictionless or surface is smooth. The smooth surface or frictionless surface means that you can ignore the friction as a force. There's always a normal force, but no friction. But then whenever the surface is rough, then you have to take the friction into account, because one of the things we have here is that the friction is, technically always there. And to say that surface is frictionless is one of those approximation simplifications that we technically do. All right, so there are two types of friction forces. Now let's talk about, okay, so now that we know that there's a friction force, there are two types of friction forces, right? So one is kinetic friction, the other one is static friction. Okay, and we're going to talk about those. We're going to talk about the differences, but kind of like very quick different definition of kinetic friction and static friction, or the differences, is this. Whenever object is in motion, so basically object is sliding on a rough surface, the friction that opposes the motion is known as kinetic friction, because kinetic means motion. So kinetic friction means that surface opposing moving object. But when object is at rest, and then you try to push the object, so right now, try to push your desk, for example. If you try to push your desk, you probably will be unsuccessful if you pushing it, with, let's say, a light force, right? Because friction prevents the object from moving, and that's a static friction. So in a way, you can think like, let's say, static means no velocity. So anytime you push an object is not moving, you're basically dealing with the static friction. That means static friction opposes your motion, opposes your force, right? Cancels your force. But when you're pushing something that is already moving and there's a rough surface, you're dealing with kinetic friction. All right. Why do we have a friction? Well, even if the surface looks relatively smooth, if you look at the microscopic level, right, you always see some, imperfections and things like that. There are bumps and things like that on the surface, you can see, right? And, interaction between them, surface and the, basically the bottom of the block and the top of this floor, right? That interaction, what, generates a frictional force, okay? That means the frictional force is due to the sort of the rough surface, okay? And in any case, what we have here is, when we say a smooth surface, we don't really say that there's no friction. We can say that smooth surface means that friction is so small we can ignore it. Not necessarily there's no force, no friction force, but we just can ignore it if comparing them. For example, if you push this box with some applied force of 30 newtons to the right, and let's say there's a friction, let me make it like a, so let's say there's a friction force opposing it is 0.05 newtons. Well, you can see it's so tiny that, we can just say, let's forget about it. So just ignore this. and just say that here's a force acting on it, right? So that's why when it's very smooth, the friction force is small, so small compared to applied forces, we can ignore it. Well, then how can we, let's say, figure out if it's a small frictional force or large frictional force? Well, we can do that by using what we call this coefficient of friction. Because the surface, when you have a surface-surface interaction, your ability to slide object depends on interaction between the block and the surface. So obviously, for example, if you have a metal block and if you have ice, you have very little resistance for you to push the object. But if you try to, let's say, have a rubber box, right, and try to push it, on a concrete surface, you're going to get a very difficult time doing that. That means this coefficient mu, in a way, represents information about roughness or the smoothness of your let's say, of your surface. Now, one of the things we have here is this mu has no units. It's just a number, and it's a number that is between 0 and 1. That means 0.2, 0.3, 0.8, 0.9. So generally, when the number is closer to 0, this represents more or less a smooth surface. Let's say 0.1, 0.2, that's a smooth surface. When the number is closer to 1, then it's a rough surface. So for example, 0.8, 0.9, that's a rough surface. Let's say 0.9 is rubber on concrete, and that definitely, means that you're gonna have a hard time pushing. So that means, and you should be able to find the table with the values of, coefficient, in the textbook. And generally, one of the things that we will see is that those values of coefficient usually, given to you in the problem, or it could be something that we are looking for. All right, so here's then what I have in terms of then a normal force. Okay, so how do we, let's say, find the static friction? Well, one of the things we need, as I said, is the coefficient. So let's say coefficient is for the static, and here's a coefficient for kinetic. And they're not usually the same. Coefficient of the static is, on average, is greater than the kinetic, because interaction, the surface-surface interaction, that coefficient changes if the block is moving or if it's at rest, And when its object is at the rest, and you just, try to push, generally the coefficient, much greater. Okay. Now, here's then what we have. In terms of then, let's say, finding the static friction or kinetic friction, another thing you need is the normal force. Okay, so you need coefficient and normal force. Because, for example, if you want to find the coefficient of kinetic friction, then what you do here is you take the coefficient of, so if you want to find kinetic friction, you take then the coefficient of kinetic friction and multiply that by normal force. And that will give you coefficient of, that will give you the kinetic friction. And kinetic friction generally is more or less, it's a constant force. That means it doesn't really change. So if I calculate the kinetic friction as, for example, 20 newtons of magnitude, it usually, might vary, like it's very tiny, but I can treat that as constant. Static friction force, on the other hand, is different. And we're going to see that in the next slide. But for example, right, so right now, if I have this applied force of, let's say, 50 newtons, and for example, then I have a kinetic friction opposing that of, let's say, that 20 newtons, put that direction as well. Then what I can do here, I can find the net force in the x direction by taking then the applied force minus kinetic friction, 50 newtons minus then 20 newtons. Both of them are horizontal, and what I get here is 30 newtons in the x direction. That's my net force. That means when you're pushing with the box with 50 newtons, you have a 20 newtons opposing, right? Opposing, let's say, dissipating force from the surface. That means it takes away the effect of the applied force. So you can see, right? Without friction, you have 50 newtons pulling, pushing the box. With friction, the effective force is only 30 newtons. So you're losing some of those, newtons, let's say, because of the friction. All right, so then again, once you use this equation, right, for the kinetic friction, it's more or less constant. Okay, you don't have to worry about does it change over time and things like that. No, as long as the block is sliding, it's in motion, same kinetic friction is, can be used. All right, so things change a little bit if you talking about static friction. Okay, so let's kind of talk about that. Here's what I have with the static friction. Static friction is a variable force. Okay, and that means it can be zero, it can be increasing, right? I mean, obviously the lowest it can be, I'm talking about the magnitude. The lowest it can be zero, and it can then increase, but it can increase only to a point. So let's look at this pictures, right? So starting with the, part A. We start with a box on the surface and at rest. Now, there are two forces acting on the box, even when the object is sitting there at rest. Well, it's on the surface, so there's a normal force, and the gravity, right? That means you have two vertical forces, normal force up, gravity down. And what you can see here is, because it's at rest, those normal force and weight technically cancel each other. That means normal force is equal to the weight. Okay. But there are no parallel to the surface forces. Well, if there are no parallel to the surface forces, well, the friction force, remember, is opposing any other parallel to the surface forces, but because there are none, there's nothing to oppose. So then static friction here is zero because there's nothing to oppose. So again, so if we're doing this graph, so let's look at this graph over here. So I have this graph where this is applied force you can think of, and this is frictional force. The y-axis represents frictional force, x-axis is the applied force. Well, when one is zero, the other one is zero. But let's say now it's tension or applied force, doesn't matter. So let's say now we pull the block with, let's say, a force of 5 newtons. All right. So here's that force of 5 newtons. What I can do here is this. Well, if I apply 5 newtons and the block is still not moving, that means that the static friction force is able to prevent the block moving by applying force of negative 5 newtons. That means if I do 5 newtons, it increases to the negative, well, again, this is kind of magnitude, right? It increases itself to 5 newtons. Well, how about if I push harder? So let's say 10 newtons. Well, I come back and push with or pull with 10 newtons. Well, if it's still not moving, it's because it's able to adjust itself to 10 newtons. All right, how about 15? Well, maybe, if it's still not moving, that means it's, adjust itself to 15 newtons. That means it's a variable force where it can increase and match your applied force. But it's not going to be able to do this forever, because one of the things we have here is how much this static frictional force can increase depends on the surface-surface interaction. So then one thing we can do here, we can calculate maximum static frictional force. And maximum static frictional force is equals to the static friction coefficient, right? Coefficient of static friction times normal force. This is the equation that we can use to calculate the maximum static friction force. For example, if the coefficient is 0.5, and let's say normal force is, let's say, I don't know, 50, right? So 50 newtons. So 0.5 times 50 newtons. So then we get maximum friction force of 25 newtons. So coefficient 0.5 represents surface interaction between box and the surface. 50 newtons is basically the normal force, which is, we can find that, but because we can see that normal force minus weight equals 0 in a vertical direction. So normal force equals to weight, and let's say it has a weight of 50 newtons. That's how I got the normal force. Well, if I have the normal force and the coefficient of friction, I can find the frictional force. That means the maximum value it can have, or the maximum value it can go up to, is 25 newtons. So that's why when I apply 5 newtons, it has no problem, opposing it that by 5 newtons. I pull 5, it pulls back 5. I pull 10, it exerts 10, they cancel each other. I pull it by 20, it pulls back with 20, and they cancel each other. Well, I pull 25, so here, see, I do 25, it can still do 25, right? Because, its maximum is 25. Well, what happens if I do 30 newtons? Well, if I apply 30 newtons, well, that's beyond what the static friction can handle, which means then I win. Tension is stronger, or the applied force is stronger than static friction, maximum static friction, so then the block starts sliding. That means it starts accelerating to the right. And as soon as it does, see, this is Fs maximum. As soon as it does, the friction right away drops down, right? Decreases, because now the box is sliding. That means I'm dealing with kinetic friction. This is F of K. And then kinetic friction is mu K times normal force. And because mu K is less than mu S, I get smaller value for the kinetic friction. That means it's much harder to push something from rest than push something that is already sliding, okay? So opposition is less, right, when the box is already sort of like, let's say, in motion. Kinetic friction is always less than static friction. So that's kind of what we have. Static friction is a variable force that opposes your motion, and it's always acting in the opposite direction, but it can only do so much because it has a maximum value. And if you push harder than that, you can make the object accelerate. All right, so here's an example for that. We have, like, as I said, right, so I'm going to do a couple of simple examples, right, to kind of demonstrate what we talked about. So here's some guy pulling a crate. Okay, so crate is my object of interest. I want to know, okay, so if somebody pulling, so let's say with the force of tension of 230 newtons, okay, will this guy be successful if the weight of this crate is 500 newtons? So if I apply 530 newtons, can I pull the crate? Can I make it, move? Is this 530 Newton enough to, to pull the crate? Well, we need to follow those steps of, vector addition of forces, right? To figure out. Here's one thing I have. Taking the crate as my object of interest. So this B over here represents the free body diagram of this. So this is my crate. Well, I have 3 agents. Person gives me a tension of 230 newtons to the right. That means I get tension force from that. Earth gives me 500 newtons weight. This is Earth, right? And then the surface, in this case, giving me a normal force. And because it's a rough surface, giving me a friction. Okay. So this is the free body diagram. Then what I have here is this. Remember, this is step 1 of always, analyzing, force problems. Step 2 would be to do the force table. So those are my forces. X component, Y component. Now what I have here is, this is my tension force. This is my normal force. This is my weight. And this is the friction. All right, so by the way, at this point, I don't know if this is a static friction or kinetic friction. And the reason I don't know is because I don't know the value of the static friction. Or, remember, I have tension as 230. See, if the static friction maximum is greater than 230, that means, so let's say 300, right? That means static friction here can exert 230 Newton force to the left and cancel this 230 tension force. Hopefully you guys understand one thing. That means, for example, if the static friction force, maximum static friction force is 300, and you pull the crate with 230, so sometimes I have questions, students asking, so how come if you pull by 230, how come the static friction is not 300? Because its maximum is 300. Well, if surface pulls, exert 300 Newton to the left, while somebody pulling 230 to the right, well, you can see, right, that means they don't cancel each other, which means the static friction is stronger than, tension force. Well, what this will mean is that the crate will start accelerating in the direction of the strongest force. Imagine you have a crate at rest, you try to pull it to the right, but instead it accelerates to the left. It doesn't happen, right? What happens here is that if you pull and it's not moving, it's because there's a 230 exactly in opposite direction. Even though it has 300 maximum, it only pulls back with the same force as your applied force. Or it only needs that to cancel it, that's it. All right, so again, the 300 is just a number that I shoot. And what I have here is, I made up that number. We're gonna, calculate that to see actually what it is. Okay, so let's see what we have. Here's a net force. Tension is in the positive direction, in a positive x direction. It has no y component. Normal force in a positive y direction, no x component. Weight has no x component, is in a negative y direction. And friction is in a negative x direction, has no y component, so we put it 0 over there. Okay. Remember, this is the net force in the x direction, and this is the net force in a y direction. So basically those are my, let's say components, right? All right, so remember, this force table gives you two equations. Here's equation 1, let me put it here. Remember, this is step 3 where we get two equations. Equation 1, net force in the x. This is tension minus friction, right? Which is basically, this is net force in the x, right? Tension minus friction equals net force in the x. Then I get equation 2, net force in the y direction, which is basically this, column over here. For that, I have normal force minus weight. Well, you can see that when you're pulling the block in a y direction, there's nothing happening. That means those normal force and weight cancel each other and you get that. But that means normal force is equal to your weight. Well, we were given that weight is 500, that means normal force is at 500 Newtons as well. I found normal force. And let's say you're given that there's a coefficient of 0.4 for that surface. So there's a coefficient of static friction of 0.4, or coefficient of friction, let's say. If I have normal force, let's say there's mu s, right? Coefficient of static friction. If I have normal force and I have a coefficient, that means one thing I can do, I can solve for the maximum static friction, which is mu s times normal force. Okay, so that if it's a mu s of 0.4 and then normal force of 500, well, that gives me 200 Newtons, which means my maximum static friction force is 200. It can only oppose up to 200. That means what happens here is when you apply tension force of 230, the maximum it can go, basically the surface can prevent is 200, and that's not enough to keep the crate at rest, and the crate will accelerate. And the acceleration of the crate then will be due to the fact that tension is stronger than static friction. As soon as the crate starts moving, the friction becomes kinetic friction, and then you don't even have to pull with that hard anymore. You can just go back and pull with 200 Newtons because that's already enough, because kinetic friction is less than static friction. All right. So that's kind of what we have with this type of problems. Here's one more example. So let's say what happens if the tension is at an angle? Will I get the same normal force? Will I get the same friction? We can see something like that in this particular example. One of the things I have here is you still have the same crate, which is 500 Newton weight. You still have the same surface, same coefficient of 0.4, let's say, right? Or in this case, mu k, so let's say mu k is 0.4. Okay. So, and let's say there's this tension force right now at 30 degrees with the horizontal. So let's see what happens that is different here compared to the previous example. Well, the difference is this. So now I have a tension, I have normal force, I have weight, and I have friction, right? It's kinetic friction because it's moving. So net force. This is my net force in the x direction. This is my net force in the y direction. Let's look at the tension. Well, tension is, if I do the free body diagram, right? So same normal force, same weight, same friction, but tension here is at an angle. And this is 30 degrees. Well, I can see that if I break it down into components, x component is t cosine 30, y component is t sine of 30. Tension is first quadrant, so plus plus. Normal force, no x in a positive y direction. Weight has no x component in the negative y direction. Friction is in a negative x direction. It has no y component. So those are my equations. Equation, so this is step 3, right? So equation 1 is the net force in the x. T cosine 30 minus kinetic friction. And then I get equation 2, which is net force in the y. And this time what I have is this, normal force plus t sine of 30 minus weight equals 0. Again, it equals to 0 because the black hole or the crate only going to be, any type of motion will be along the x-axis. Well, what I get here is this. In equation 2, then normal force equals to then weight minus t sine of 30. Which means if the weight is 500 newtons, the normal force equals 500 minus some number, whatever it is, right? The normal force will be less than before, which means less than 500. So let's say it's 400, for example. Well, if the normal force is 400, then you can see, if you remember, right, f of k equals mu k times normal force. Well, now f of k will be less than before, okay? So even though right now tension here is probably less than before because it's t cosine 30, right? But so is the kinetic friction because, normal force decreases because of the y component of the tension. So you can see, right, number of things change, but still, if the t cosine 30 is greater than kinetic friction, so let's say if t cosine 30 is greater than kinetic friction, then what you will get here is mass times horizontal acceleration. That means you have a non-zero net force, which means your system, the crate, right, of mass m will start accelerating. And acceleration in the x direction equals net force in the x direction divided by the mass, which means t cosine 30 minus kinetic friction divided by the mass. You can then calculate the acceleration. All right, here's one more force that we will we'll have to consider. If you remember, we talked about free fall. Free fall, we used approximation or just simplification, remember? So we always said that in order for us to consider motion as a free fall, ignore air resistance. Because here's what I have. If object is falling, if I ignore air resistance, the only force acting is the gravitational force. Remember, we call it weight right now. Which means weight is the only vertical force and it equals mass times acceleration, because that's my net force in the y direction, and this is just, one force, and it was negative, right? Remember, weight itself was mg, so that's why you can see, right, if you cancel that, your acceleration equals negative g. So that's what we end up having before, which means if you have no air resistance, your object will always have this vertical negative g acceleration, and as long as it's falling, it's going to speed up, and it's going to increase its speed, increase its speed, increase its speed until it hits the ground. But here's what I have. For example, you drop something from a very high tower, or maybe like I don't know, airplane or something like that. Imagine if you drop something from airplane, that object is going to accelerate all the way down to the ground. And that's going to be humongous final velocity when it hits hits the ground, because it's going to be speeding up the entire time. Well, it's going to do a lot of damage if that's the case. Well, luckily for us, that's not the case, because we have air resistance, air molecules that slow down things. So for example, when you have an object of mass m and you drop that object, well, initially only gravity acting, only its weight. So then accelerate, so then net force in a y direction is just a negative weight. But then because of the air molecules and things like that, then there's also a new force. Let's call this F of D, which is we call drag force. And then the value for F of D is, so let's say here's F of D, drag force. It's equals to some kind of coefficient, D, which we call drag coefficient, times velocity or speed squared. That's the equation for this drag force. And you can see, right, it depends on the speed. When you drop your object from rest, drag force is 0, so the gravity pulling it down. As it starts speeding up, the drag force increases. And it increases until at some point, here's the object during its motion where the gravity is acting on it down, right? But then this drag force acting upward, it increases to the point where it equals to your weight. It cannot be greater than your weight, because you've never seen the object that was falling suddenly slow down, stop, and then start accelerating upward. It never happens. That means the maximum drag force can be is to be equal to your weight. Well, this is, let's say, dv squared equals mg. And you can see that from here, v is equals to mg over d, then square root. So this velocity is known as a terminal velocity. That means terminal velocity, again, vt terminal is equals to square root of your weight divided by this drag coefficient. That means the object that is falling eventually will stop accelerating and then just fall at constant velocity because of air molecules. Air molecules never gonna slow it down or stop, right? But what happens is that you drop the object, initially it's speeding up, but then it's gonna stop speeding up. It's gonna just fall with the constant velocity. Okay, and that velocity is known as a terminal velocity, and that's the equation for that. All right, so the last thing we have in this chapter is elastic forces. That means we're gonna be considering forces due to the elasticity property of the objects. And the best system to consider is the spring force. Imagine you have a spring, okay? Imagine you have a spring that is what we call in a relaxed form. That means you're not stretching the spring, you're not compressing the spring, just basically it's in relaxed form. But what we do here, we attach, right? We attach a block. Again, block at this point just attached without stretching or compressing the spring. So the point where your system sitting there without stretch or compression of the spring is known as the equilibrium position. That means here, that position I take as x equals 0, because that's my sort of relaxed position of the end of the spring, let's say. The other end is connected to the wall and so never changes its position. As long as the system is in equilibrium, there is no elastic forces. But as soon as I grab the block and I pull it to the right, so you can see, right, grab the block and I pull it to the right with some distance x. As soon as I do that, the spring itself gonna try to exert force on the block to pull it back to the equilibrium. So we call that, restoring force, because it tries to restore the system back to equilibrium. If you pull the block to the right, this restoring force to the left. One thing, if I pull it twice the distance, the restoring force becomes twice the magnitude, which means that this elastic restoring force is proportional to distance. I pull it 3 times x, force becomes 3 times. I pull it 4 times x, force becomes 4 times. That means it directly proportional to the distance from equilibrium. Well, one of the things we have is that as you go from, proportionality sign to equal sign, you introduce a constant. And that constant is a spring constant. So one thing it represents here is this. So let's say you pull the spring, you pull the, the spring block system, right? To 1x, to 2x, and 3x, and there's a force proportional to the x. But also one of the things you have here is you probably have seen in your life, right? So in different cases, right? There are different springs. Some are very stiff, some are kind of loose, right? So then what we have here is then we can say that this elastic force is equals to the directly proportional to the x, but there's also this k, which is the proportionality constant. And then k is information about the stiffness of this particular spring. Stiffer springs have a larger k value. Looser springs have a smaller k value. So let's say your car springs might have like 5,000 or 8,000, 10,000 in terms of that k value, where just a regular laboratory, springs might have like 10, 20, 100, a value for k. But k as a unit, it's in newtons over meters, right? Newtons per meters. And in a way, this equation represents that. This F spring, which is the restoring force from the spring, equals this constant K, the spring constant, times delta L, and delta L represents distance of stretch or compression of the spring relative to equilibrium. Okay, and the delta L should be in meters, K is in newtons per meters, right? And then you get the force, from that, right? One of the things we have here is we always have a lab in a regular semester where we given the spring and we have to determine the spring constant K. And the easiest way to do that is, hang the spring vertically, like over here, right? Hang the spring vertically and attach some kind of weight holder. Let's say some kind of weight holder. And then once you attach a weight holder, you wait until your system in equilibrium. You can see, right? So the weight holder is very light. So, very light, so that what you get here is this position, you can say that as either x equals 0 or y equals 0, right? So that's my equilibrium position. That's the, spring being it's in, let's say, unstretched condition. Then I apply force. The way I apply force, I put like a block that has 20 newtons, weight. When I put that block starts stretching the spring. You can see, right? Starts stretching the spring. But you can see from this free body diagram. So here's the spring. Initially, it has this weight of the block pulling it down. But as soon as the spring is moved from its equilibrium, there's a restoring force bigger and bigger and bigger, because more you move from equilibrium, stronger this force, until this F spring at some point is equals to, so you can see, right, F spring becomes equal to the weight, which is mg, and your system comes to equilibrium, it stops. Well, that means F spring equals mg. Well, F spring is K times delta L. That means K times delta L is equals to the weight of the block. Well, what is delta L? Delta L is this, by how much the spring was stretched until it comes to rest again. So that means you can measure it. So for example, it's a 12 Newton, applied force, which is the weight, and 1 centimeter, displacement. So then I can use this relationship where I can say that then K is equals to the mg divided by delta L. This is 12 Newtons divided by 0.01 meters, right? And well, this is 1200 Newtons per meters. That's basically my spring constant K for that. That means by using the known weight and measuring how much it displaces the spring from equilibrium, you can solve for the spring constant K. All right, so that's basically the last thing we had about forces that we will be using. This last slide just talks about some of the forces that we have in nature. Gravitational interaction is one interaction that we talk about in this class. In physics 7, we're going to consider electromagnetic interaction, which is the forces between between two objects. If they are charged, they exert electrical forces. There's also strong and weak interaction, and those are basically at subatomic level. We don't really go into that. So the idea here is that physicists try very hard to unite all those forces into one a single physics law, but so far they are unable to, or it's extremely difficult to try to find conditions where you can unite them all into single, let's say, concept or single equation. So that's why right now we have 4 different ones, even though some of them have way of bringing them together, because electromagnetic is a combined electricity and magnetic interactions. So technically their weak interaction can also be combined. So it's electro weak interaction. So, but generally gravitational interactions are difficult to combine with anything else. So far, scientists are struggling to kind of have a one unified, let's say, a law that describes all the interactions together. All right, so this concludes this chapter 5 concept video. Part 2 will be, I'll make part 2 and upload soon, which will be just, going over the examples or, some of the examples in this chapter. And I will then work and make the chapter 6, which, will be uploaded shortly, either today or tomorrow.